Right now, almost 500 million miles from the sun, there is an ocean no one has ever seen. It moves in total darkness beneath a roof of ice, miles thick. An ocean that has never felt a single ray of sunlight, never known a sunrise, never been touched by the warmth the rest of us take for granted. And yet, it is not frozen solid, and it may not be dead. Somewhere down there, in water kept liquid by a hidden fire, the same handful of ingredients that gave rise to every living thing you have ever known may be coming together in the dark. This is Europa, a moon of Jupiter smaller than our own, and it has quietly become one of the most promising places in the entire solar system to search for life beyond Earth. We know the water is there. We are increasingly sure the heat is there. We have good reason to think the chemistry is there. The only question left, the one that keeps certain scientists awake at night, is brutally simple. Is anything swimming in that dark? For a long time, that question felt like pure fantasy, a thing for dreamers and storytellers and late-night wondering. It does not feel like fantasy anymore, because for the first time in history, we have built a machine, aimed it across the solar system, and sent it to find out. If that question grips you the way it grips me, and you want to go deeper into it, leave a like and subscribe. It would really mean a lot to us. To feel the strangeness of Europa, you first have to feel how wrong it is that this ocean should exist at all. Out where Jupiter rolls through space, the sun is no longer the great warm presence that rules our sky. It is a bright star, fierce but distant, throwing only a feeble fraction of the light and heat it pours onto Earth. At that distance, a small world should be a frozen ruin, a ball of rock and ice locked in a cold so deep that nothing moves, nothing flows, nothing lives. By every reasonable expectation, Europa should be exactly that. A dead, silent, frozen wasteland, a snowball drifting in the dark. The surface, in fact, looks the part. It is one of the smoothest surfaces in the solar system, a vast shell of ice cracked and veined with long reddish lines, stretching unbroken in every direction, lit only dimly by a sun too far away to do much good. Stand on that surface, if you somehow could, and you would see a frozen plain under a black sky, with Jupiter hanging enormous overhead, and you would feel certain you were standing on a tomb. And you would be wrong, because beneath your feet, beneath all that ice, something is moving. The secret of Europa is not in the moon itself, it is in the giant it orbits. Jupiter is not just a big planet, it is a world so massive that everything around it bends to its will, and Europa lives close enough to feel the full force of that gravity. As the moon swings around its giant in an orbit that is not a perfect circle, Jupiter's pull on it is constantly changing. Stronger when Europa is near, weaker when it is far. That shifting grip squeezes and stretches the entire moon, flexing it like a ball worked in a restless hand. And there are other moons too, Io and Ganymede, locked into a steady gravitational rhythm with Europa, tugging on it again and again at just the right moments, keeping its orbit slightly off-round so the flexing never stops. All that bending and kneading does what bending and kneading always do. It creates friction, and friction creates heat. Deep inside Europa, far from any sunlight, this tidal heat warms the interior enough to melt the underside of the ice. The result is the thing that should not be there. Not a thin film of meltwater, not a few hidden pools, but a global ocean of liquid salt water, wrapped all the way around the moon, sealed under its frozen shell. To appreciate how astonishing that hidden ocean is, it helps to look more closely at the engine that keeps it from freezing, because it is unlike anything that warms our own world. On Earth, the sun does the work. On Europa, the work is done by motion and resistance. by the relentless physics of a moon caught in a gravitational tug-of-war. Europa does not orbit Jupiter alone. It shares its neighborhood with other large moons, and 3 of them are locked into a precise and beautiful rhythm. For every 4 times the innermost of the 3 circles Jupiter, the middle one goes around twice, and the outer one once, a clockwork relationship so exact that the moons line up and pull on one another in a repeating pattern, over and over, for as long as anyone can imagine. That steady, synchronized tugging is what keeps Europa's orbit from settling into a lazy circle. The other moons will not let it. They keep nudging it, holding its path slightly stretched, so that as Europa swings around Jupiter, the distance between them rises and falls, and the giant's grip tightens and loosens with every loop. You can see the raw power of this same mechanism by looking at Europa's inner neighbor, the moon Io, which feels Jupiter's flexing even more strongly. Io is the most volcanically active body in the entire solar system, a tortured world where hundreds of volcanoes erupt without rest, throwing plumes of sulfur hundreds of miles into space and paving the surface again and again with fresh lava. Io has no hidden ocean. It is far too hot and dry for that, squeezed so hard that its insides have partly melted into rock. But Io is the proof, written in fire, that this gravitational kneading is real and that it can release staggering amounts of heat. Europa, sitting a little farther out, feels a gentler version of the same forces, not enough to melt rock, but more than enough to melt ice. The very process that turns Io into a furnace turns Europa into a sealed sea. It is a remarkable thing to realize that an ocean can be heated not by any star, but by the simple, ceaseless mechanics of orbits, that gravity itself, working through the geometry of moons, can light a fire in the dark deep enough to keep an ocean alive for billions of years. It is easy to lose track of just how small and how far away this world really is, and holding both facts in mind at once is part of what makes it so haunting. Europa is not a planet. It is a moon, and not even a large one, a touch smaller than our own familiar moon, a modest ball of rock and ice you could cross in a journey shorter than many we take on Earth. And yet this small body, orbiting roughly 5 times farther from the sun than we do, may hold more liquid water than our entire planet. Out there, sunlight arrives faint and cold, taking the better part of an hour to cross the distance, so weak by the time it reaches Europa that high noon on its surface would look like a deep, dim twilight to our eyes. The moon is locked in its orbit, so that one face is forever turned toward Jupiter, the way our own moon keeps one face always turned toward us. Stand on that Jupiter-facing side, and the giant planet would never move from its place in the sky, hanging huge and banded and silent overhead, filling a great patch of the heavens, turning slowly through its cloud bands while the distant sun rises and sets around it. Picture that scene for a moment, because it captures the strangeness of the place. A frozen plain stretching to a close horizon, cracked and stained, under a black sky. A sun too small and far to give any real warmth. And dominating everything, that vast striped world, the source of both the danger and the heat, looming over the ice like a permanent storm hung in the sky. It is a landscape of almost unimaginable cold and stillness on the surface, a place that looks for all the world like the very definition of dead. And the deepest irony of Europa is that this still, frozen, forbidding surface is nothing but a lid, a frozen roof over the most promising body of liquid water we know of beyond our own planet. Everything that matters, everything we are hoping for, lies hidden underneath, where the lid keeps its secret from the sky. It is hard to grasp the scale of that ocean until you put it next to our own. The seas of Earth, all of them together, Every gulf and trench and open expanse hold a certain vast amount of water that has defined our entire planet and every creature in it. Europa's hidden ocean is thought to hold more than that. By many estimates, this single moon, smaller than our own moon, may carry twice as much liquid water as all the oceans of Earth combined, perhaps even more. And it is not a shallow sea. Below the ice, the water may plunge down for 60 miles or more before it reaches the rocky floor, a depth that dwarfs the deepest trench in any earthly ocean. Picture that for a moment. A world where the entire surface is a frozen sky, and beneath it falls an ocean so deep that our own Pacific would be a puddle by comparison, an abyss of black water held in perpetual night, pressed under crushing pressure, and yet kept liquid and moving by the fire of Jupiter's grip. That is Europa. Not a frozen rock, a buried ocean world. For a long time, all of this, the ocean, the heat, the depth, was inference and argument rather than something we had directly confirmed, and you might reasonably ask how we became so confident about a sea no one has ever seen. The answer comes from two very different kinds of evidence, one written across the moon's surface and one hidden in its response to Jupiter's magnetism. Start with the surface, because even from a distance it tells a strange story. Most old dead worlds in the solar system are saturated with craters, pockmarked by billions of years of impacts that nothing has ever erased. Europa is almost smooth. Across its entire face there are remarkably few craters, which means the surface must be young, geologically speaking, constantly being erased and renewed. Something is repaving Europa, wiping away the scars of impacts, and the most natural explanation is an ocean below feeding fresh ice to the surface, cracking and refreezing and reworking the shell so that old wounds do not last. Look closer at that surface, and the story deepens. Europa is laced with long, dark lines that run for thousands of miles, great cracks and ridges that crisscross the ice in sweeping arcs, stained a reddish-brown by something welling up from below. In places, the smooth plains give way to wild, jumbled regions where the ice looks broken into rafts, blocks that seem to have shifted and tilted and frozen back into place, as though a frozen sea had shattered, drifted, and set again. These features are hard to explain without liquid water beneath the ice, water that rises into the cracks, that lets great slabs of the shell float and move, that carries dissolved salts up to the surface where they leave their colored stains. Reading Europa's surface is like reading the surface of a frozen lake in spring and seeing in its cracks and heaves the unmistakable signs of moving water underneath. The second kind of evidence is subtler and, in its way, even more convincing, and it came from a spacecraft that orbited Jupiter and made repeated close passes by Europa years ago. Jupiter has a powerful magnetic field, and as Europa moves through it, that field changes from the moon's point of view. Here is the key. If you have a layer of salty, electrically conducting liquid inside a body and you subject it to a changing magnetic field, that liquid responds, generating a magnetic field of its own in reaction. When the spacecraft measured Europa's magnetism, it found exactly that kind of induced response. The signature of a global layer of salty, conducting fluid beneath the surface. In other words, the moon answered Jupiter's magnetism in a way that only a hidden salty ocean could. It was as close to reaching out and touching that ocean as we have ever come, a measurement that turned the buried sea from a strong suspicion into something very near a certainty. The surface showed us that water had moved. The magnetism showed us the water was there, salty and global, waiting beneath the ice. There is a reason that water, of all the substances in the universe, sits at the center of every conversation about life, and Europa shows off that reason beautifully. Water is an extraordinary substance, far stranger and more accommodating than we usually notice. It stays liquid across a wide range of temperatures, giving chemistry room to work. It dissolves an enormous variety of other substances, which is why we sometimes call it a universal solvent, allowing countless different molecules to mingle and react within it. Living things on Earth are mostly water, and every cell in your body is essentially a tiny pouch of salty water in which the chemistry of life unfolds. Wherever we look for life, we look first for liquid water, not because we lack imagination, but because water is so well suited to the task that it is the natural place to begin. And Europa, against every expectation for a world so far from the sun, has water in oceanic abundance. There is also a quiet, lucky quirk of water that makes Europa's whole arrangement possible, and it is one we take for granted every winter. Water is unusual in that its solid form, ice, is lighter than its liquid form. Ice floats. This is why a frozen pond ices over on top while staying liquid below, the surface ice forming a lid that insulates the water beneath and keeps it from freezing solid. The very same thing is happening on Europa, on a colossal scale. The shell of ice that seals the moon is not just a barrier, it is a blanket. It traps the heat rising from the interior, holding it in, allowing the ocean below to stay liquid even as the surface freezes hard as stone in the brutal cold. Without that floating, insulating lid, the heat might escape, and the ocean might freeze through. With it, Europa becomes a sealed, self-warming sea, its frozen roof both hiding and protecting the water that could, just possibly, be alive. A small peculiarity of a common molecule turns out to be one of the reasons this distant ocean can exist at all. And here is where the story turns from astronomy towards something far more personal. Because an ocean alone is not yet a reason to dream of life. Cold, dark water is just cold, dark water. What makes Europa burn in the imagination of scientists is what we learned, not out there, but right here at home, in the depths of our own seas. For most of our history, we believed something that seemed obvious beyond question. We believed that life, all life, ultimately runs on sunlight. Plants drink the sun and turn it into food, and everything else eats the plants or eats the eaters, so that even a lion on the plain or a fish in the sea is, in the end, living on captured sunshine. Take away the sun, we assumed, and you take away the foundation of everything. The deep ocean floor, far below the reach of any light, was imagined as a barren desert, a lifeless plain of mud where almost nothing could survive. We were certain of it. And then, only a few decades ago, we went down to look, and what we found rewrote the rules of biology. In the darkness at the bottom of our own ocean, miles down, where no sunlight has ever reached, and the pressure would crush most machines, explorers found cracks in the seafloor where the planet's inner heat leaks out. Around these cracks rise strange chimneys of mineral, hydrothermal vents, gushing hot, chemical-rich water into the freezing dark. And clustered around these vents, in a place that should have been a desert, they found not emptiness but a riot of life. Towering colonies of pale tube worms taller than a person, swaying in the current. Ghostly crabs and shrimp. Mats of bacteria thriving in scalding, toxic water. An entire bustling community of living things, complex and abundant, living in total darkness, utterly cut off from the sun, depending on it for nothing at all. It was one of the most stunning discoveries in the history of science, and its meaning was enormous. Life did not require sunlight. Life required energy, and where the sun could not provide it, life had found another way. It is worth dwelling on that discovery in our own ocean. because it is one of the great turning points in the history of science, and it is the entire reason Europa keeps people up at night. Until the late 1970s, the deep seafloor was assumed to be a near lifeless desert. Then, a small research submarine carrying a few scientists descended into the dark along a volcanic ridge on the ocean floor, far below the reach of any sunlight, and what its lights revealed astonished everyone aboard. Rising from the seabed were chimneys of dark mineral, belching shimmering, superheated water, and swarming around them was an explosion of life so dense and so bizarre that the researchers could hardly believe what they were seeing. There were clams the size of dinner plates, blind white crabs, and most striking of all, great forests of tube worms, creatures with brilliant red plumes standing in white stalks taller than a person, swaying in the warm chemical current. These tube worms turned out to be even stranger than they looked. The largest of them have no mouth, no gut, no way of eating in any ordinary sense at all. Instead, their bodies are packed with vast colonies of bacteria, and it is these bacteria that do the feeding, pulling energy out of the chemicals in the vent water and sharing the proceeds with their host. The whole ecosystem, from the microbes to the worms to the crabs that prey on them, rests on a foundation that has nothing to do with the sun. It rests on chemistry rising from inside the earth. This was the revelation that changed everything. It proved that a complete, thriving web of life could be built on the planet's internal energy alone, in total darkness, sealed away from the surface world. And it did something even bolder to our imagination. Many scientists now suspect that places like these, hot, mineral-rich, chemically active boundaries between rock and water, may be exactly the kind of setting in which life on Earth first began, billions of years ago, in the dark. Hold those two ideas together, and you can feel why Europa burns so brightly in the scientific mind. If life can not only survive, but possibly begin at the boundary between hot rock and dark water, and if Europa has precisely such a boundary at the bottom of its ocean, then Europa is not merely a place where transplanted life might cling on. It is a place where life might have arisen on its own, by the same kind of process that may have given rise to it here. The vents in our deep sea are not just an encouraging analogy. They are a glimpse of the very conditions under which a world can come alive. And they exist, very probably, on the floor of an alien ocean 500 million miles away. Everything we learned in the dark of our own sea points, like an arrow straight at Europa. The trick these deep creatures use has a name, and it is the key to everything that makes Europa exciting. Instead of photosynthesis, drinking light, the organisms at the vents use chemosynthesis, drinking chemistry. The hot water rising from inside the planet is loaded with dissolved minerals and chemical compounds, and certain microbes have learned to pull energy directly out of those chemicals, building the base of a food web from the raw materials of the rock and the heat. They do not need a star. They need water, they need warmth, and they need the right chemistry seeping up from below. They need exactly the conditions that we now believe exist at the bottom of Europa's hidden ocean. If the rocky floor of that ocean has cracks where Europa's inner heat leaks out, and there is every reason to think it might, then those cracks could be ringed with the very same kind of chemistry that feeds the gardens of life in our own deep sea. The question becomes almost unbearable. If life found a way to thrive in the cold dark of our ocean floor, with no sun and no sky, then what, exactly, is stopping it from doing the same thing on Europa? There is one more ingredient on the list that is easy to overlook because it is not a thing at all, but a quantity, and that is time. Life, as best we understand it, did not appear on Earth in an instant. It emerged through an unhurried interplay of chemistry over long ages, countless reactions unfolding and combining until, somewhere, somehow, a line was crossed from mere chemistry into something that could grow and copy itself. What we do know about our own world is striking. Life seems to have taken hold remarkably early in Earth's history, not long, in geological terms, after conditions first allowed it. That tells us something hopeful, though not certain. It hints that when a world has water and warmth and the right chemistry, the beginnings of life may not demand an impossibly rare stroke of luck, but may follow more readily than we once feared, given enough time for the chemistry to do its slow work. Europa has had time in abundance. Its ocean has been there, churning in the dark, for the better part of the solar system's entire history. Billions upon billions of years of warm water meeting mineral-rich rock at the seafloor, of chemistry stirring and recombining without pause. Whatever processes can happen in such a place have had an almost unimaginable stretch of time in which to happen, over and over, across the whole vast floor of a global sea. None of this guarantees anything. A world can have all the ingredients and all the time and still, for reasons we may never fully understand, remain empty. But it does mean that if life was ever going to take hold on Europa, it has not been for lack of opportunity. The stage has been set, the materials supplied, and the clock has been running, quietly, patiently, for longer than we can easily comprehend. That is the dream, and it is a serious dream, not a wild one. But before we get carried away, we have to be honest about what we actually know and what we are only hoping. We have not seen anything alive on Europa. We have not sampled its water. We do not have a single image from beneath its ice. What we have is a list of ingredients, and that list is remarkable. We have liquid water, almost certainly, in enormous quantity. We have energy, in the form of tidal heat and very likely chemical energy at the seafloor. We have the raw chemical elements that life as we know it is built from, because they are common throughout the solar system and there is no reason Europa would lack them. And we have time, vast stretches of it, 4 billion years and more, during which that ocean has been churning quietly in the dark. Water, energy, chemistry, and time. Those are the conditions under which we believe life arose on Earth. Europa appears to have all four. That does not mean life is there. It means that if it is not, we will have to ask why a place with all the right conditions stayed empty, and that question would be almost as profound as finding life itself. It is worth being precise about what those ingredients really are, because the word habitable gets used loosely, and it deserves better. When scientists talk about what life needs, they are usually pointing at a short list. First, a liquid, almost always liquid water, because life as we understand it runs on chemistry, and chemistry needs a medium in which molecules can move, meet, and react. Frozen solid, nothing happens. Boiled away, nothing happens. Liquid water is the stage on which the molecular dance of life takes place, and Europa appears to have it in staggering abundance. Second, the right raw materials, the handful of chemical elements that living things are built from. The carbon and hydrogen and oxygen and nitrogen and a few others that form the backbone of every biological molecule. These elements are common across the cosmos, forged in stars and scattered through space, and there is no reason to think Europa lacks them. Third, a source of energy, some flow of usable power that life can tap to do the work of staying alive and growing, whether that is sunlight or chemical energy or the heat and minerals of a vent. But there is a fourth thing, subtler than the rest, that matters just as much. Life does not feed on energy in the abstract. It feeds on differences, on imbalances, on gradients between one state and another. A battery is useful only because there is a difference between its two ends. In the same way, life needs a world that is not perfectly settled and uniform, but one where energy-rich chemicals meet energy-poor ones, where hot meets cold, where the products of one process can fuel another. The boundary at the bottom of Europa's ocean, where mineral-laden water from the rock meets the chemistry of the sea above, is precisely the kind of restless, unbalanced frontier where such gradients arise. When hot water moves through certain kinds of rock, it can drive reactions that release exactly the sort of energy-rich compounds that simple life loves to consume. We have good reason to think those reactions are happening, or have happened, on Europa's seafloor. Added all together, water, raw materials, energy, and the precious imbalance that lets energy do useful work, and Europa checks every box on the list. Whether anything has actually taken advantage of all that is the open question. But the table, as far as we can tell, is set. So if Europa is this promising, if it has been sitting out there with all the right ingredients for billions of years, an obvious question arises. Why haven't we already gone? Why aren't there cameras drifting through that ocean right now? Lights sweeping across the dark, beaming images home. The answer is that Europa is not just hard to reach. It is one of the most ferociously hostile places we have ever tried to study, guarded by forces so violent that for decades they kept us at arm's length. The first guardian is invisible, and it is the very same giant that gives Europa its ocean. Jupiter is not only a gravitational titan, it is a colossal generator of radiation. Its enormous magnetic field traps and accelerates charged particles into belts of radiation so intense that they make the fiercest radiation zones around Earth look gentle. Europa orbits right inside this storm. The surface of the moon is bathed, day and night, in a sleet of high-energy particles that would be lethal to a human being in a shockingly short time, and that tears apart the delicate electronics of any spacecraft foolish enough to linger there too long. To stand on Europa unprotected would not be a slow danger. It would be a swift sentence. To understand why that radiation is so merciless, you have to grasp the sheer scale of the thing that produces it. Jupiter's magnetic field is not just strong, it is monstrous. The largest and most powerful magnetic structure of any planet in the solar system, reaching out millions of miles into space, so vast that if it glowed visibly in our night sky, it would appear larger than the full moon. This field acts like an enormous trap, capturing charged particles and whipping them up to tremendous speeds, accelerating them until they form belts of radiation far fiercer than anything around Earth. Europa orbits squarely within this invisible inferno. There is no shelter on its surface, no atmosphere thick enough to shield it, nothing to stand between the moon and the ceaseless rain of high-energy particles. A person on that surface would absorb a lethal dose with terrible speed, and unshielded electronics would degrade and fail in short order. This is the price Europa pays for living so close to its giant, and it is the single greatest obstacle to studying the moon up close. And yet, in one of the great ironies of this whole story, the same radiation that makes Europa so deadly may also be one of the keys to its potential for life. When that relentless particle storm strikes the surface ice, it does not merely sterilize it. It also breaks water molecules apart, splitting them and building up reactive, oxygen-bearing compounds in the frozen shell. Oxygen and oxidants like these are powerful chemical fuels, and on Earth they are deeply tied to the rise of active, energetic life. Now imagine those compounds, created at the surface by radiation, slowly being drawn downward over the ages, carried into the ocean as the ice cracks and churns and refreezes. If that downward delivery is happening, then Jupiter's deadly radiation is also, in a strange way, fertilizing the sea below, feeding the ocean a supply of chemical energy from above to match the chemical energy rising from the vents below. A world squeezed between two sources of fuel, oxidants drifting down from a radiation-blasted sky and minerals welling up from a fiery floor, is a world with the kind of chemical richness that life could exploit. The guardian at the gate may also be a provider. The very force that keeps us out may help keep the ocean alive. The second guardian is the ice itself, and it is not the kind of ice you might imagine from a frozen pond. At the brutal temperatures of Europa's surface, hundreds of degrees below anything we ever feel, water ice does not behave like the slick, brittle stuff we skate on. It becomes harder than you would believe, behaving more like rock than like anything we call ice. And it is not a thin crust. The frozen shell that seals Europa's ocean may be many miles thick. In places, perhaps 15 miles or more of solid, rock-hard ice standing between the surface and the water below. To reach that ocean directly, you would have to send a machine that could bore or melt its way down through the equivalent of a buried mountain range, surviving the cold, the pressure, and the radiation screaming down from above the entire time. We have never built anything that could do that. Not yet. It is almost as if Europa were a sealed vault, its treasure locked behind walls of stone-hard ice and a moat of deadly radiation, a world that does not want to be found. And the strange logic of exploration is that a vault guarded this fiercely is exactly the kind of vault you most want to open, because barriers this strong tend to surround something worth protecting. There is a strange poetry in that arrangement, a moon whose treasure is guarded by the very forces that make it precious. The radiation that would kill us is born of the same giant whose gravity keeps the ocean warm. The ice that locks the water away is also the blanket that keeps it from freezing, and the shield that protects whatever lives below from the lethal storm above. Every barrier standing between us and that ocean is, from another angle, part of what makes the ocean possible in the first place. Europa does not merely hide its sea, it hides it behind walls that are themselves the reason the sea exists. To reach the water, we must get past the very conditions that created and sustain it. Perhaps that is fitting. The things most worth finding are rarely the things easiest to reach, and an ocean that has stayed sealed and undisturbed for billions of years, protected from us and from everything else by cold and ice and radiation, has a kind of integrity to it, a wholeness that we approach with both hunger and respect. We want to know what is in there. We have wanted to know for as long as we have understood that an ocean was in there at all. And the difficulty of the task, far from discouraging us, has only sharpened the desire. Because some part of us senses that a place this well defended, this patiently kept, is exactly the kind of place where the answer to our oldest question might finally be waiting. For a long time, all we could do was stare. We watched Europa from a distance through telescopes, and we caught fleeting glimpses during brief flybys, when earlier spacecraft passing through the Jupiter system swung close enough to snap a few precious images before hurrying on. Those glimpses were enough to set the imagination on fire. They showed us the cracked, mysterious surface, hinted at the ocean below, and left us hungry for more, like a treasure spotted through a keyhole that we could not yet open. But staring through a keyhole was all we could manage, because to do more, we needed a machine built specifically for this fortress, designed from the ground up to survive everything Jupiter could throw at it and still do real science. Building such a machine took decades of dreaming, arguing, planning, and engineering. And then, in the autumn of 2024, after all those years of waiting, humanity finally answered Jupiter's challenge and launched its best attempt yet to break into the vault. Those decades of staring were not idle, and it is worth honoring the long line of machines that brought us to this point. Because our knowledge of Europa was built up patiently, one distant encounter at a time. The first true glimpses came from spacecraft that swept through the Jupiter system on their way elsewhere, passing the giant and its moons and sending back the earliest close pictures of worlds that had been, until then, mere points of light. Even those fleeting passes were revelations, showing for the first time that Europa's face was strangely smooth and cracked, unlike the battered, crater-pocked surfaces of so many other moons, and planting the first seeds of suspicion that something unusual lay beneath. Later, a dedicated spacecraft settled into orbit around Jupiter and spent years studying the giant and its family of moons, swinging past Europa again and again. It was this long, patient campaign that gathered the crucial evidence, the detailed images of the fractured surface, and above all the magnetic measurements that betrayed the hidden ocean's presence. Piece by piece, encounter by encounter, the case for a sea beneath the ice grew from a wild idea into a serious scientific conclusion. Each mission handed its findings to the next generation of scientists, who refined the questions and dreamed up the instruments that might answer them. The journey to Europa has been a relay run across many decades, each spacecraft carrying the baton a little farther, until at last the evidence was strong enough and the will firm enough to justify building a machine designed for Europa alone. Everything we are about to attempt rests on the shoulders of those earlier visitors, on the slow accumulated work of turning a frozen point of light into a destination worth crossing the solar system to reach. Its name is the Europa Clipper, and it is no ordinary spacecraft. It is the largest spacecraft ever built for a planetary mission, a craft whose solar wings, unfurled, stretch wider than a basketball court, spread that broad precisely because sunlight is so weak out at Jupiter that it needs an enormous reach to gather enough power. But the real genius of the Clipper is not its size, it is its strategy, a clever answer to the radiation trap that has guarded Europa for so long. The Clipper will not orbit Europa directly, circling close and soaking up the deadly radiation until its electronics fail. That would be a slow form of suicide. Instead, it will orbit Jupiter itself, swinging in long, looping paths through the system, and on each loop it will dive in for a fast, close pass over Europa, gathering as much data as it can in those precious minutes, and then race back out into the calmer space farther from Jupiter, where it can recover before the next dive. Again and again it will repeat this maneuver, dozens of close encounters over the course of the mission, each one a quick raid into the danger zone, followed by a retreat to safety. It is a cosmic game of hit and run, designed so that the spacecraft is never in the worst of the storm long enough to be destroyed. The looping, hit-and-run path is only half of the spacecraft's defense against the radiation. The other half is built into the body of the machine itself, the most sensitive and vital electronics, the brain and nervous system of the craft, are gathered together and enclosed inside a thick vault of metal, a shielded heart designed to absorb the worst of the particle storm and protect the delicate components within. Everything about the spacecraft, from its materials to its circuits to the way its instruments are mounted, had to be designed with Jupiter's radiation constantly in mind, hardened and tested against an environment that would wreck ordinary hardware in days. This is part of why a mission like this takes so many years and so much effort to build. You are not just making a spacecraft, you are making a spacecraft that can keep working while being slowly cooked by one of the most hostile environments in the solar system. And that can do it for years, through dozens of dives into the danger zone, without failing. There is something almost paradoxical in the whole endeavor. A machine sent to a place so dangerous that it must spend most of its time fleeing, designed to learn the secrets of a world it can never safely linger near. Each close pass over Europa is a brief, precious window, a few hours at most in which every instrument works at full stretch, gathering all it can before the spacecraft must retreat. The data from each dive is collected, stored, and then slowly beamed back across the vast distance to Earth during the calmer stretches of the orbit. A trickle of hard-won information crossing hundreds of millions of miles to reach the people waiting for it. Building a mission that works this way, that turns its own vulnerability into a careful rhythm of approach and escape, is a triumph of patience and ingenuity. It is the product of countless engineers solving countless problems, each one standing between us and the ocean we are trying to reach. The fortress of Europa demanded a key forged with extraordinary care, and it took us decades to forge it. Launched in 2024, the Clipper is now crossing the immense gulf between us and Jupiter, a journey of years, using the gravity of other worlds along the way to slingshot itself outward and build up the speed it needs. It is not due to arrive until around the end of this decade, and that long wait is part of the story too. A reminder of just how far away this ocean is and how much patience the search for it demands. But when it arrives, it will carry a suite of instruments that turns it from a mere camera into something far more powerful. A machine built not just to look at Europa, but to look into it. The crown jewel is a kind of radar that can see through ice. By sending radio waves down into the frozen shell and listening for the echoes, this instrument can map what lies beneath the surface, tracing the thickness of the ice, finding pockets of liquid water trapped within it, and perhaps even glimpsing the boundary where the ice gives way to the ocean below. For the first time, we will not just be studying Europa's frozen skin. We will be peering through it, building a picture of the hidden structure that has been sealed away from us for the entire history of our species. That ability to see through the ice matters enormously. But there may be an even more direct way to learn what the ocean holds, and it depends on whether Europa, like at least one other icy moon, sometimes lets its sea escape. For years, scientists have searched for signs that Europa vents plumes of water into space through the cracks in its shell, and there have been tantalizing hints. Sensitive observations have, on occasion, suggested faint sprays of water vapor rising from the moon, here and then gone, glimpsed, and then not seen again. A fresh look at old data gathered during an earlier spacecraft's close pass even turned up signs that the craft may have flown through such a plume without anyone realizing it at the time. None of this is fully settled. The plumes, if they exist, appear to be intermittent and faint, hard to catch, present one day and absent the next, which is exactly what you would expect from cracks that open and close as the moon flexes. But if those plumes are real, they are a gift almost too good to believe. To sample Europa's ocean, we would not necessarily have to land, drill, or melt our way through miles of ice. We could simply fly through a plume and catch the spray, letting the moon hand us a sample of its hidden sea, lofted into space and waiting to be collected. The chemistry of those droplets would carry the signature of the ocean below, its salts, its compounds, perhaps the faint chemical fingerprints that hint at life or its building blocks. This is part of what makes the coming exploration so exciting. The spacecraft is equipped to seize such a chance if it comes, to taste a plume should it cross one, turning a fleeting eruption from a distant ocean into hard data. Few prospects in all of planetary science are as thrilling as the idea that a sealed alien sea might, now and then, breathe a little of itself into the void, right where a machine of ours is waiting to read it. And the Clipper does more than see. it can taste. Europa, it turns out, may not keep all its secrets locked beneath the ice. There are signs that the moon, at least sometimes, vents its ocean into space. Cracks in the shell, flexed open and shut by the same tidal forces that heat the interior, may at times allow plumes of water vapor to erupt from below, spraying tiny droplets of the hidden ocean up through the surface and out into the vacuum above. If those plumes are real and the clipper can fly through one, then something extraordinary becomes possible. The spacecraft carries instruments that can catch those droplets and analyze them, reading the chemistry of the ocean without ever drilling a single inch. We could learn what salts the water carries, what compounds are dissolved in it, whether the building blocks associated with life are present, all from a sample flung into space by the moon itself. It would be like a sealed vault occasionally puffing a little of its contents out through a crack, and a clever investigator flying past to catch that puff and read it. We would not have to break into the ocean. The ocean would, now and then, come out to us. Seeing through the ice and tasting the plumes are the most dramatic of the spacecraft's talents, but they are far from the only ones, and it is the combination of many different senses working together that gives the mission its real power. The craft carries cameras of remarkable sharpness, able to map Europa's surface in far finer detail than we have ever managed, capturing the cracks and ridges and jumbled terrains close up, building a portrait precise enough to pick out features only tens of feet across. With these images, scientists will be able to study exactly how the surface has been reshaped, where the ice seems youngest and most active, and where the ocean below may be interacting most closely with the shell. The craft also carries instruments sensitive to heat, able to scan the frozen surface for unusually warm patches, places where the ice might be thinner or where water might have risen close to the top not long ago. A warm spot on that frozen face would be a clue, a hint of where the ocean comes nearest to the surface and where a future mission might one day try to break through. Other instruments will read the light reflected from the surface to determine what it is made of, sorting out the salts and other compounds painted across the ice, compounds that may have come straight from the ocean below and that could carry hints about its chemistry. Still others will measure the moon's magnetic and gravitational behavior with new precision, refining our picture of how deep the ocean is, how salty, and how far beneath the ice it begins. No single one of these instruments could answer the great question on its own. But together, cross-checking and reinforcing one another, they form something far more powerful than any of them alone. One traces the shape of the hidden ocean, another tastes its chemistry, another maps the surface that seals it, another reads the heat leaking from within. Layer by layer, measurement by measurement, they will assemble the most complete portrait of Europa we have ever had, transforming a distant point of light into a known world, mapped and measured and understood as never before. And every layer of that portrait brings the central question into sharper focus. Not yet, perhaps, the answer to whether Europa is alive, but the firm foundation on which that answer will one day rest. This is the crucial thing to understand about what the Clipper is really hunting for. It is not, in its first mission, going to land on Europa, melt through the ice, and send a submarine into the deep. That dream may come one day, but it is not this dream. What the Clipper is built to do is answer a more fundamental question first. It is built to determine whether Europa is truly habitable, whether the ocean really has the water, the energy, and the chemistry that life would need. It is searching for the conditions of life, the setting in which life could exist, rather than for the creatures themselves. That distinction matters, and good science insists on it. Confirming that a world is habitable is not the same as confirming that it is inhabited, but it is the necessary first step, the thing you must establish before any later mission could go hunting for actual organisms. If the Clipper shows that Europa has everything life requires, it transforms the moon from a hopeful guess into a confirmed target, a place we would then have every reason to return to and search in earnest. And if it finds hints of the chemistry of life in those plumes, the pressure to go back and look closer would become almost irresistible. That irresistible pull toward going back raises a question that scientists are already thinking hard about, long before it becomes urgent. Suppose the day comes when we decide we must get beneath the ice and search the ocean itself for life. How would we even do it? And what would we owe to the world we were entering? Getting through the ice is a staggering challenge in its own right. The shell may be miles of rock-hard frozen water, and any machine sent to cross it would have to melt or drill its way down through that barrier, powering itself for the long descent, surviving the cold and the pressure, and somehow keeping in contact with the surface far above so that whatever it found could be sent home. Engineers have sketched ideas for such machines, probes that would melt slowly downward through the ice, trailing a thread of cable behind them, eventually breaking through into the ocean to release a small submarine into the dark. None of this exists yet. All of it lies at the very edge of what we can imagine building. But the fact that serious people are sketching it at all is a measure of how seriously Europa is now taken. And then there is a responsibility that weighs on everyone who thinks about this, a duty easy to overlook in the excitement. If we send a machine into Europa's ocean, we must be absolutely certain that we do not carry our own life there with us. Earth's microbes are tough and clinging, and they ride along on everything we build. To arrive at a pristine alien ocean and accidentally seed it with bacteria from our own world would be a disaster in two directions. It could harm whatever native life might exist there, and it would forever ruin our ability to tell what we had found, because we could never again be sure whether a microbe in that water was a true European or a stowaway from home. For this reason, missions to worlds like Europa are held to strict standards of cleanliness, and any future probe meant to touch the ocean would have to be cleaned and sterilized to an extraordinary degree. There is a quiet humility in this, a recognition that we are not entitled to barge carelessly into another world. If Europa holds life, that life belongs to Europa, and our task would be to discover it without destroying it. The search itself demands a kind of restraint, a promise to look without spoiling, to learn without leaving a careless mark on a world that has gone undisturbed for billions of years. Still, it is impossible to study Europa for long without your mind drifting past the careful language of habitability and toward the wilder question underneath it all. If something does live in that ocean, what on earth, or rather what not on earth, would it be like? Here we leave the firm ground of what we know and step into informed imagination, and it is worth being clear about that line. No one can tell you what lives on Europa, because we do not know that anything does. But we can reason about what life there might be like, guided by what we understand about how living things adapt to their surroundings, and the picture that emerges is strange and beautiful. The first and most important fact is the darkness. Europa's ocean is a world of absolute, permanent night. No light has ever reached it from above, and so any life evolving there would have grown up over billions of years in conditions where sight, as we know it, would be useless. On Earth, eyes evolved because there was light to see by. In a place with no light at all, there would be little reason to grow eyes, and much reason to develop other senses instead. So picture, if life is there, creatures that do not see the way we do, that may have no eyes at all, because eyes would be a waste in a world without light. Instead, they might be exquisitely tuned to vibration, feeling the faintest stir in the water, sensing the approach of another creature, or the pulse of a distant vent through the trembling of the sea itself. They might read their world through chemistry, tasting the water constantly, following faint chemical trails the way a creature on land might follow a scent. Their bodies might be soft and translucent, like the jellyfish and delicate drifting things that haunt the dark zones of our own oceans. Shapes built not for fighting light, but for moving gently through heavy, lightless water. And in that perfect darkness, the one place light might still appear is the light a creature makes itself. On Earth, many deep-sea animals glow, producing their own cold light through chemistry inside their bodies, using it to lure prey, to startle predators, to signal to a mate. In the black ocean of Europa, if anything has evolved to glow, that self-made light would not be for seeing the world. It would be a private language written in the dark, a flicker of meaning in an ocean that has never known any other kind of light. When we try to imagine what life in Europa's ocean might be like, our only real guide is the life that already thrives in the darkest, strangest corners of our own. And our deep sea is a far stranger place than most people realize. A vast realm of perpetual night that covers most of our planet, and that we have only begun to explore. Down there, where no sunlight falls, evolution has produced creatures that would seem more at home in a dream than on Earth. There are fish that dangle glowing lures in front of their own mouths to draw prey out of the blackness. There are animals that flash and pulse with living light, signaling to one another in codes of glow and shadow. There are soft, transparent, drifting things, and creatures with enormous, sensitive eyes to catch the faintest spark, and others that have abandoned eyes entirely in favor of feeling the water for the slightest tremor. Life in our own dark has solved the problem of living without the sun in 100 inventive ways. Every one of those solutions is a hint about what might be possible on Europa. The creatures of our deep sea show us that darkness is no barrier to richness, that an ocean cut off from sunlight can still brim with variety and strangeness and ingenuity. They show us that life, given energy and time, will find ways to sense, to hunt, to communicate, and to endure in conditions that seem impossibly hostile. If our own lightless depths can produce such wonders, then the lightless depths of Europa, given billions of years and a steady source of energy, might produce wonders of their own, shaped by rules we can only guess at. We cannot say what swims in that alien sea, if anything does. But we are not guessing in a vacuum. We are guessing with the example of our own dark ocean before us, an ocean that has taught us, again and again, never to assume that darkness means emptiness. It is natural to wonder whether such an ocean could hold anything more than microbes, whether there could be larger creatures down there, real animals drifting and hunting in the deep. Honesty requires caution here, because the realistic expectation, the thing scientists would actually bet on if pressed, is that any life on Europa is most likely microscopic, simple, single-celled. That alone would be earth-shattering. But there are reasons the door is not entirely closed on something grander. One of them is oxygen. The radiation that batters Europa's surface, harsh as it is, does something interesting to the ice. It breaks water molecules apart and creates oxygen and other reactive compounds in the frozen shell. Over long ages, some of that oxygen might work its way down into the ocean below, carried by the slow churning of the ice and the cracking and refreezing of the surface. Oxygen is a powerful source of energy for life, the very fuel that allowed complex, active animals to flourish on Earth. If Europa's ocean has been quietly receiving oxygen from above for billions of years, then in principle it could support more than just microbes. It could, possibly, sustain larger and more complex things, creatures drifting through the abyss, living off that chemistry, evolving in total isolation. We do not know if this is so, but we cannot yet rule it out, and that uncertainty is part of what makes Europa so haunting. Let yourself imagine, just for a moment, what it would be like to make that journey down, to travel from the frozen surface all the way to the ocean floor, through a world built entirely in layers of darkness. You would begin on the surface, in a cold so deep it is hard to picture, under a black sky, where Jupiter hangs vast and banded, and the distant sun is just a brilliant star. Beneath your feet, the ice. You start to descend, and at first it is hard and brittle, the surface ice fractured by ages of flexing. As you go deeper, the ice changes, growing slightly warmer, slightly softer, pressed by the weight above, perhaps threaded here and there with pockets of briny slush where salt has lowered the freezing point. Down and down you go, through mile after mile of frozen shell, in absolute darkness, the surface receding far above you, until at last the ice begins to give way and you reach the boundary that no eye has ever seen, the place where the solid shell meets the liquid sea. And then you are in the ocean itself. The water is utterly black, and it stretches downward beneath you for tens of miles, a column of dark water deeper than any abyss on Earth. As you sink through it, the pressure builds relentlessly, growing to a force that would crush an ordinary submarine like an empty can. There is no light here, none at all. Only the slow movement of currents driven by the heat far below, the gentle churn of an ocean stirred by the moon's inner fire. You drift downward through this lightless immensity, hour after hour, mile after mile, until finally, far beneath the ice, you approach the floor, the rocky heart of the moon. And here, if our best guesses are right, the darkness would not be empty. Here would be the vents, chimneys of mineral rising from the seabed, warm water shimmering out of them. The chemistry of the rock meeting the chemistry of the sea. This is the place where everything we hope for would have to live. The one warm, rich, chemically active frontier in all that cold, dark water. If life is anywhere on Europa, it is most likely here, gathered in the faint glow of its own making around these hidden fires, in a place so far from the sun and so far from us that the mind can barely hold the distance. We have never been there. We may not get there for a very long time. But it is real. It is waiting. And now, at last, we have begun the journey toward it. Whatever lives there, if anything does, would be a kind of life that has never had any contact with us or with our world. Think about what that really means. Every living thing you have ever encountered, from the largest whale to the smallest germ, from the trees outside your window to the bacteria in your own body, all of it belongs to a single family. All of it shares the same deep chemistry, the same basic molecular machinery, the same long story stretching back to a common origin on this one planet. We are all, every organism on Earth, branches of one tree. But life on Europa, if it exists, would not be a branch of our tree. It would be a separate tree entirely, sprung from its own independent beginning, growing in isolation in the dark for billions of years, owing nothing to Earth, knowing nothing of the sun, shaped by a history completely apart from ours. It would be a second, independent example of life, and that is something we have never seen. For all our science, for all our searching, we still have exactly one example of life in the universe, the one we are part of. Europa offers the possibility of a second, and a second example would change the meaning of the first. There is a dizziness that comes from contemplating how long that separate experiment, if it exists, has been running. Europa's ocean is not young. It has likely been there, liquid and churning, for the better part of the moon's history, billions upon billions of years. If life took hold in it early, then whatever swims there now is the product of an unbroken chain of living things, stretching back across an almost incomprehensible span of time, every generation shaped by the one before. All of it unfolding in total isolation, sealed away beneath the ice with no knowledge of any other world. On Earth, that same depth of time carried life from simple single cells to the staggering variety we see around us, to forests and coral reefs and the creature now taking in these words. We have no idea what so vast a stretch of evolution might produce in an ocean so different from ours, under such different rules, but the mere possibility is enough to make the imagination real. And there is a further, stranger thought. We tend to assume that any life we find would be built more or less like ours, using the same kinds of molecules, the same basic chemistry. But there is no guarantee of that. Life that arose independently, on a world with its own conditions, might have made different choices at the deepest level, might be assembled from molecules arranged in ways we have never encountered, might run on a biochemistry subtly or even profoundly unlike the one shared by every living thing on Earth. If so, then finding it would not just add a second example to our list, it would stretch our very definition of what life can be, showing us that the single pattern we know is one option among many rather than the only way to be alive. That is part of why even the smallest discovery on Europa would ripple so far. It would not merely tell us that we have company. It might tell us that life is more inventive, more various, more open-ended than anything our single example could ever have revealed. We would be holding, for the first time, a second version of one of the universe's deepest sentences, and learning that it could be written in more than one language. Because here is the weight that the smallest discovery on Europa would carry. If we were to find even a single living microbe in that hidden ocean, one tiny organism swimming in the dark, it would be among the most significant discoveries in the entire history of our kind. And the reason is not the microbe itself, but what it would tell us about the universe. As long as life is known only on Earth, we cannot say whether life is common or rare, whether worlds like ours are full of living things, or whether we are a strange and lonely exception. We have one data point, and one data point tells you almost nothing about the pattern. But if life appeared a second time, independently, on another world right here in our own solar system, then the picture changes completely. It would suggest that life is not a rare and solitary exception that happened only once in an unimaginably empty cosmos, but something that can take hold wherever the conditions are right, a natural outcome of the right water and the right warmth and the right chemistry given enough time. And if that is true here, around our own sun, then it is very likely true around countless other stars as well. The night sky would stop being a field of distant lights and become a field of distant possibilities, each point a place where, perhaps, something is alive. It is worth pausing to feel what that would actually do to something as ordinary as looking up at the night sky. Right now, when we step outside on a clear night and see the stars, we see beauty, distance, mystery, but also, if we are honest, a certain emptiness, a sense of vast cold spaces with ourselves as the only known spark of life in all of it. Finding life in the ocean of Europa would quietly rewrite that experience for everyone, for good. Each of those distant points of light would become not just a star, but a place where life might also have found a way. A sun perhaps warming worlds of its own, where something stirs in a hidden sea. The night sky would change from a beautiful void into a crowded, living frontier, and we would never quite be able to look at it the same way again. That is the strange power of a discovery like this. It would not be locked away in a laboratory or confined to the pages of a journal. It would reach into the most common human moment there is, the simple act of looking up, and fill it with new meaning. A child gazing at the stars would grow up in a universe known to contain more than one living world, and that knowledge would settle into the imagination of our whole species, shifting, in some deep and lasting way, our sense of where we stand and who shares the dark with us. We have always filled the night sky with our stories and our longings. To learn, at last, that it might truly be filled, that life is not ours alone, would be among the most profound changes in outlook our kind has ever undergone. And it might begin with a single microbe in the black water of a moon we can already name. That is the quiet revolution hiding inside this whole endeavor. For most of human history, the question of whether we are alone in the universe was a matter for philosophers and poets, unanswerable, suited only to wondering. It is becoming, for the first time, a question we can actually investigate, with instruments and missions and data, a question that might receive a real answer within the lifetimes of people alive today. Europa is at the very heart of that shift. It is close enough to reach, promising enough to justify the effort, and now, with the clipper on its way, it is finally within our grasp. We are moving from an age of pure speculation about cosmic loneliness into an age of genuine search, and that is a threshold our species has never crossed before. Whatever the answer turns out to be, the simple fact that we can now ask it seriously and act on it marks a change in our relationship to the universe that is hard to overstate. It is worth remembering how old and how deep the longing behind all this really is. For as far back as we have records, human beings have looked at the lights in the night sky and wondered whether other worlds might be inhabited, whether the points of fire overhead might be suns with worlds of their own, holding creatures we could scarcely imagine. For most of that long history, the wondering had nowhere to go. There was no way to test it, no way to look closer, nothing to do but dream and argue and stare upward. The idea of life beyond our world drifted through stories and speculations for ages, always just out of reach, a question that seemed permanently locked away from any real answer. Generation after generation inherited the same mystery and passed it on unsolved, a question as old as curiosity itself. What makes our own moment so extraordinary is that this ancient wondering has, almost without our noticing, turned into something we can act upon. The very same question that haunted our distant ancestors, whether we are alone, is now a target for engineering and exploration. Something we can pursue with radar and spectrometers and spacecraft, rather than only with imagination. Europa is one of the sharpest points where that transformation is happening, where a dream as old as humanity is being handed, at last, the tools to become knowledge. There is a kind of awe in standing at that threshold, in realizing that we may be among the first people who could actually learn the answer to a question everyone before us could only ask. Those who gazed up in ages past would scarcely believe what we are now able to do, that we have built a craft and sent it out to a frozen moon of Jupiter for the specific purpose of finding out whether we have company in the cosmos. We are living through the moment when one of the oldest questions ever asked stops being merely a question, and it is worth pausing on how strange and recent this whole way of thinking is, because the very idea that a frozen moon could be a home for life would have seemed absurd not so long ago. For generations, when scientists imagined where life might exist beyond Earth, they thought in terms of a narrow band of space around a star, a comfortable zone where a planet could be warm enough for liquid water on its surface, not too close and not too far, lit and heated by its sun the way Earth is. Anything outside that cozy ring was written off as too cold and dark for life. By that old logic, Europa, far out in the frozen reaches beyond the warm zone, was hopeless. But the discovery of life around our own deep sea vents shattered that thinking. It showed that a world does not need to bask in starlight to host life. It needs an internal source of energy and liquid water, and those can exist in places a star's warmth never reaches, kept alive instead by the heat of gravity and the chemistry of rock. Europa took the old map of where life could be and tore it wide open, revealing that the truly habitable places in a solar system might not be the sunlit worlds at all, but the hidden oceans buried in the dark. And this revolution in thinking does not stop at the edge of our own solar system. If hidden oceans beneath ice are common here, around our own sun, then there is every reason to expect them around other stars as well, in numbers we can scarcely guess at. The galaxy is filled with stars, and around those stars circle untold numbers of planets, and around many of those planets, surely, circle moons, and out in the cold reaches of those distant systems, far from the warmth of their suns, some of those moons may carry frozen shells over hidden seas of their own. We cannot see them. They are far too small and far too distant for any telescope we have to detect directly. But the logic that gave Europa its ocean, the simple physics of gravity and flexing and heat, does not care which star a system orbits. It would work just as well around a sun 1,000 light-years away as it does around ours. That thought stretches the imagination almost past its limit. It suggests that the universe may be quietly studded with dark, buried oceans, countless hidden seas locked beneath ice on worlds we will likely never visit and may never even know exist, each one a possible cradle, each one sealed away in a darkness as complete as Europa's. Most of them will keep their secrets forever, beyond the reach of any instrument we can build. But their sheer likely number changes the emotional weight of the whole question. If even a small fraction of those hidden oceans cradle life, then the cosmos is not the sterile void it can sometimes seem, but a place where living things stir quietly in the dark, in more places than we could ever count. Europa is the one such ocean we can actually reach, the single accessible example of what may be a vast and unseen multitude. To explore it is, in a sense, to take the measure of all the rest, to learn from the one hidden sea within our grasp what the uncountable others beyond our reach might hold. Once you understand that, the solar system begins to look like a very different place, far richer in possibility than the cold, dead expanse we once imagined. Because Europa is not alone. It turns out that buried oceans may be common out among the giant planets and their moons. Around Saturn, there is a small moon that actively sprays great geysers of water from its south pole, plumes that spacecraft have flown directly through, tasting in them the signs of a salty ocean and the chemistry that life might use. There are other large moons, around Jupiter and Saturn both, that are suspected of hiding oceans of their own beneath thick shells of ice. What once seemed like a desert of barren rocks and frozen wastes is starting to look like an archipelago of hidden seas, world after world carrying its own dark ocean sealed beneath the surface. If even one of these turns out to hold life, the implication is staggering. It would mean that the warm, sunlit surface worlds like our own may be the exception, and that most of the living places in the universe are oceans no eye will ever see, locked away in eternal darkness, kept alive by the slow fire of their planet's gravity. We may be the strange ones, the surface dwellers, blinking in the rare and unusual light of an open sky. To see just how far this idea now reaches, it is worth taking a tour of the other hidden seas that may be scattered through our own solar system. Because Europa, remarkable as it is, has turned out to be only one member of a growing family. Travel outward to Saturn, and you find a small, bright moon that has become almost as tantalizing as Europa itself. This little world does something Europa only hints at. From great cracks near its south pole, it sprays enormous jets of water out into space. Continuous geysers feeding a faint ring of icy particles around its planet. A spacecraft that spent years studying Saturn flew directly through those plumes, again and again, and sampled them, and what it found was thrilling. The jets carry salt, they carry simple organic compounds, and they carry signs of the kind of chemistry that, at the bottom of that moon's ocean, might be driven by warm water meeting rock. Here was a world handing us samples of its hidden sea for free, flinging them into space for any passing spacecraft to catch. If anything strengthened the case that small icy moons can hide habitable oceans, it was this. But the family does not end there. Saturn's largest moon is a world unlike any other, wrapped in a thick golden haze, with rivers and lakes and seas on its surface, though these are made not of water but of liquid methane, flowing under a frigid sky. And beneath that exotic surface, this moon too is thought to hide a deep ocean of ordinary water, buried under its crust. Back at Jupiter, the largest moon in the entire solar system, bigger even than some planets, is believed to hold its own vast ocean sandwiched between layers of ice, and a separate mission is already on its way out to study it and its icy siblings. Other moons, around both giants, are suspected of harboring water in their depths as well. Add them all up, and a new picture of the solar system emerges, one in which liquid water, the precious requirement for life as we know it, is not the rare treasure of a single lucky planet, but a common feature of the cold outer worlds, locked away inside one frozen moon after another. We grew up believing we lived in a solar system with one ocean world, our own. We are coming to understand that we may live in a solar system full of them, most of them sealed in darkness, any one of which might hold the answer we are seeking. That realization reframes the search at Europa as part of something much larger. Europa is the most accessible and arguably the most promising of these hidden oceans, the natural first place to look, but it is a representative as much as an individual, a test case for a whole class of worlds. Whatever we learn there about how oceans persist beneath ice, about whether the chemistry of life can arise in such places, will reach far beyond Europa itself. If we find that Europa's ocean is habitable, we gain reason to believe that many others may be too. And if, someday, we find life in one of these buried seas, we will have to confront the possibility that the cold, dark, water-rich outer reaches of planetary systems are the single most common habitat for life in the universe, vastly outnumbering the warm, sunlit surfaces like our own. Europa, in that case, would be remembered not just as a fascinating moon, but as the doorway through which we first walked into a far larger and stranger inhabited cosmos than we had ever dared imagine. There is something humbling in that thought, and something thrilling at the same time. We have spent our whole existence assuming that the bright, warm, sunlit conditions we evolved in are the natural standard for life, the obvious model for what a living world should be. Europa whispers that we might have it exactly backwards. The cold, the dark, the crushing pressure, the sealed and silent depths, these might be the ordinary cradle of life across the cosmos. And our own open-air world of sunshine and weather and visible horizons might be the unusual case, a rare arrangement that we mistake for the norm only because it is the one we happen to know. To search Europa, then, is not only to look for neighbors, it is to test our deepest assumptions about what life needs and where it belongs, to find out whether we have been imagining the universe in our own image when the truth might be far stranger and far darker and far more full of water than we ever supposed. This reversal of perspective, the dawning suspicion that we might be the unusual ones, is worth sitting with, because it overturns an assumption so deep that we rarely even notice we hold it. We naturally imagine that the conditions of our own world are the standard against which all other worlds should be measured, that a planet's worth as a home for life is judged by how much it resembles Earth, with its open skies and its surface seas and its gentle sunlight. But Europa suggests that this Earth-shaped lens may be quietly misleading us. The features that make our world feel like the obvious model, the visible sun, the breathable air, the weather, the bright open horizon, might be incidental rather than essential. The particular traits of one kind of habitable world rather than the requirements of all of them. Life may not care about sunlight or sky at all. Life may care only about liquid water, usable energy, and time, and those three things can be found in places that look nothing like home. If that is true, then in searching for life we may have been looking, for a long time, in a way that was subtly skewed toward finding more of ourselves, scanning for warm, sunlit, Earth-like worlds, while overlooking the cold, dark, sealed oceans that might be the more common cradle. Europa is a correction to that bias, a reminder to widen the search, to look past the comfortable image of a second Earth and consider the strange, frozen, water-filled worlds that bear no resemblance to home and yet may be every bit as alive. It teaches a kind of humility about our own assumptions, an awareness that the universe is under no obligation to arrange its life in forms we find familiar. The most important living worlds out there might be utterly unlike ours, hidden beneath ice, lit by no star, and we will only find them if we are willing to let go of the idea that life must look like what we already know. Of course, none of this is settled, and it is important to hold the wonder and the caution together rather than letting one crowd out the other. The clipper might arrive at Europa and find an ocean that is habitable in every way we can measure, and still we would not know whether anything actually lives in it, because measuring habitability is not the same as detecting life. We might find that the ocean is real and deep and warm and rich in chemistry, and be left standing at the edge of the answer without quite reaching it, our appetite sharpened but not satisfied. Or the clipper might surprise us in the other direction, revealing that something we counted on is missing, that the energy is too scarce or the chemistry too thin, that the ocean, for all its promise, is a place where life never took hold. Either outcome would be valuable. Either outcome would teach us something profound about how life begins and where it can survive. The search does not fail if it does not find life on the first attempt. It only fails if we stop asking, if we lose the patience and the curiosity to keep looking. And everything about the long, careful, decades-spanning effort to reach Europa suggests that we are not about to stop. There is one more question that hovers over all of this, quieter than the others and harder to answer, and it has nothing to do with engineering or chemistry. Suppose we succeed. Suppose one day we confirm that something lives in the ocean of Europa. What then? What do we owe to a form of life that arose entirely apart from us, in the dark, knowing nothing of our existence? It is tempting to imagine that discovery as a simple triumph, a flag planted, a box checked. But it would be something far more complicated and far more humbling than that. It would force us to ask what right we have to study, to sample, to disturb a living world that has done perfectly well without us for billions of years. It would raise the question of whether some places ought to be approached with great care, observed gently and from a distance, rather than poked and prodded and carried home in jars. These are not questions science alone can answer. They are questions about who we want to be as we step out into a universe that may not be as empty as we feared. And perhaps that is the deepest gift of a place like Europa, even before we know what it holds. It asks us to grow up a little, to picture ourselves not as the only living thing in a dead cosmos, free to do as we please, but as one form of life among possibly many, with responsibilities that come with that knowledge. The very prospect of neighbors changes how we ought to behave. The way knowing a house is occupied changes how you approach its door. For most of history, we could indulge the notion that the universe was ours alone, a stage with a single cast. Europa, and the worlds like it, gently dismantle that notion and replace it with something humbler and richer. The possibility that we are part of a much larger story, one we are only beginning to read. Whether or not we ever find a single living cell beneath that ice, simply taking the question seriously, simply preparing ourselves to meet whatever is or is not there, has already begun to change us. It has made the universe feel less like an empty room and more like a vast, dark sea, with who knows what moving quietly in its depths. It helps, too, to sit with just how patient this kind of exploration has to be, because the timescales involved are almost as humbling as the distances. A mission like this is measured not in days or weeks, but in decades. Years of design and construction came before the launch. Years of travel across the solar system come after it, the spacecraft creeping outward toward Jupiter, looping past other worlds to borrow their gravity and gain speed. Then years of work once it arrives, loop after loop, flyby after flyby, slowly assembling a portrait of the moon from thousands of fragments of data. The people who first dreamed of a mission like this are not all the same people who built it. And some of those who built it may not be the ones who see its richest discoveries. This is science conducted on the scale of careers and generations. A relay race in which the baton is passed from one set of hands to the next, all of them working toward an answer none of them can rush. There is a particular kind of devotion in that, a willingness to begin something you may not personally finish, to plant a question whose fruit will ripen long after, simply because the question is worth answering. It is hard, from the comfort of solid ground, to feel the sheer remoteness of the place we are reaching toward, but the distances involved are part of what makes this search so daunting and so strange. Jupiter is so far away that even light, the fastest thing there is, takes the better part of an hour to travel between it and Earth. That means that when the spacecraft eventually makes its close passes over Europa, the people guiding the mission cannot steer it in real time. By the time a signal saying what the craft is doing reaches Earth, and a reply travels back, the moment has long since passed. The spacecraft must carry its own instructions, execute each delicate maneuver on its own, gather its data alone in the dark, and only later send the results home across that immense gulf. A faint whisper of radio crossing hundreds of millions of miles to be caught by antennas on the ground. Every image, every measurement, arrives already old, a message from a machine that was, by the time we read it, somewhere else entirely. There is a peculiar loneliness in that, and a peculiar trust. We send these machines out beyond the reach of our help, knowing that if something goes wrong in those crucial minutes near Europa, no one can intervene in time. They are on their own, far from home, doing the most important work of their existence in solitude and silence. And we wait. We wait years for them to arrive. And then we wait again, pass after pass, for the slow accumulation of data that will, bit by bit, answer our questions. The whole enterprise runs on a patience that is almost meditative in its depth, a willingness to set something in motion and then to wait, sometimes for a decade or more, for it to bear fruit. In an age that prizes speed and instant answers, there is something almost defiant about a project measured in decades and distances this vast. A quiet insistence that some questions are worth any amount of waiting. And the question truly is worth answering, perhaps more than almost any other we can ask. Whether we are alone is not an idle curiosity. It touches the deepest sense we have of our own place in things. For as long as we have looked up at the stars, we have wondered whether anyone, anything, looks back. Whether the universe is a vast empty hall in which we are the only voice, or a crowded place teeming with life of which we are only one small part. That wondering runs through every culture and every age. What is new, what is genuinely unprecedented, is that we are no longer only wondering. We are reaching out, building the instruments, sending the machines, gathering the evidence that might, at last, turn an ancient question into a settled fact. And of all the places where that fact might first reveal itself, this small, cracked, frozen moon, with its buried ocean and its hidden fire, stands among the most likely. The answer to one of the oldest questions our species has ever asked may be waiting under the ice of Europa, in water that has never seen the sun. And there is something almost vertiginous about realizing how close we are standing to a possible answer. For thousands of years, the question of cosmic company was the very definition of the unanswerable, a thing you could believe or doubt but never test, a matter of mood or conviction rather than evidence. To be alive now, at the precise moment when that ancient uncertainty is beginning to give way to actual investigation, is a rare kind of privilege. We did not choose to be born into this particular hinge of history. The brief window in which our tools finally grew sharp enough to reach across the solar system and ask a frozen moon whether it is alive. But here we are, and the question that every previous generation could only wonder about is, for us, becoming something we can pursue. It will not be answered all at once, and it may not be answered in the way we expect. The most likely path is slow, a gradual accumulation of evidence, each mission narrowing the possibilities, each measurement bringing the picture into slightly sharper focus, until one day the weight of what we have learned tips from suspicion towards certainty. Europa may be the place where that tipping happens, or it may be one step on a longer road that leads somewhere else entirely. Either way, the search itself has already changed something. It has taken the oldest and loneliest of human questions and turned it into work, into a project, into a thing we do rather than merely a thing we feel. And whatever the answer turns out to be, whether the ocean of Europa is barren or teeming, the very act of going to find out is one of the most hopeful things our species has ever done. Imagine the moment, years from now, when the data comes home and tells us that Europa's ocean has everything life requires. Picture the quiet in the room when the radar maps confirm the liquid water beneath the ice, when the analysis of a plume reveals the chemistry of habitability, when the case for Europa as a living world grows from a hope into a near certainty. That moment would not be the end of the search. It would be the beginning of a new and even bolder chapter, the chapter in which we start seriously planning how to go back, how to get beneath the ice, how to send something down into the dark to look for life itself. And it would change, in a deep and permanent way, how every one of us sees the night sky. Jupiter, that bright wandering point of light that humans have watched for thousands of years, would no longer be just a distant giant. It would be the home of a living ocean, a world where, against every old expectation, life found a way in the dark. And we would know that we share our own solar system, the small patch of space we call home, with another living world. Step back from Europa for a moment and consider what the whole effort says about the strange creatures undertaking it, about us. We are, after all, talking about a species that evolved on the surface of one small planet, under one ordinary star, and that has spent only the briefest sliver of its existence even capable of understanding what a moon or an ocean truly is. And yet here we are, building machines the size of buses, hardening them against radiation we cannot see, hurling them across hundreds of millions of miles of empty space, all to answer a question that brings us no food, no shelter, no obvious advantage. We are doing it for almost no reason except that we need to know. That hunger to understand, to look beyond the edge of what is useful and ask what is true, is one of the most remarkable things about our kind. It has driven us down into our own ocean trenches and out toward the planets, and now it is carrying us to the doorstep of a frozen sea 500 million miles away. There is something quietly magnificent in that, and something deeply cooperative too. No single person could build a mission like this, or even understand all of it. It takes thousands of people across many years, scientists and engineers and builders and dreamers, many of whom will never meet, each contributing a small part to a shared act of reaching. It is the kind of thing our species does at its best, when we pool our patience and our curiosity and our care toward a goal larger than any one life. To send a machine to Europa is to make a statement about what we value, that we would rather know than not know, that we would rather look than turn away, that the question of whether we share this cosmos with other life is worth years of effort and the work of countless hands. Whatever Europa turns out to hold, the simple fact that we chose to go and ask is a kind of answer in itself, a measure of who we are and what we are still willing to wonder. But for now, all of that is still ahead of us, still wrapped in if and might and perhaps. For now, the ocean of Europa rolls on in its darkness exactly as it has for billions of years, indifferent to our hopes, sealed beneath its mountain of ice, lit by no sun and watched by no eyes. The cracks open and close, the tides flex the moon, the hidden heat seeps up from the rocky floor, and whatever is down there, whether it is barren water or a teeming, glowing alien sea, it keeps its secret still, as it has kept it through all the long ages before we existed, and learned to wonder about it. The difference, the only difference, is that now we are coming. After all the centuries of staring through the keyhole, after all the dreaming and the doubting, a machine of our making is crossing the dark toward that frozen world, carrying instruments to peer through the ice and taste the breath of the ocean and tell us, finally, what kind of place this is. We have spent our whole history asking whether we are alone. For the first time, we are close enough to listen for an answer. It is a quiet thing, that listening, and easy to underestimate. There will be no sudden announcement carried on the wind, no voice from the deep declaring itself. If the answer comes, it will come as data, as careful measurements gathered pass after pass, as patterns slowly emerging from the readings of instruments crossing a frozen moon hundreds of millions of miles away. It will come the way real answers usually come. Gradually, cautiously, checked and rechecked before anyone dares to believe it. And yet, however undramatic the arrival, the meaning would be anything but small. Somewhere in that slow trickle of numbers might be the first sign that we are not the only place where the dark learned how to hold life. So we listen, in the only way we can, by building the machines and sending them out and waiting for what they bring back. We have done the hardest part already. The deciding to go. The choosing to take the question seriously enough to act on it. The rest is patience. And patience is something this search has demanded from the very beginning. The ocean of Europa has kept its secret for billions of years, and it can keep it a little longer while we make our slow approach. But the approach has begun, and that changes everything. After all the ages of wondering, we are no longer only looking up and asking. We are on our way. And maybe that is the truest way to hold all of this, not as a promise that we will find life, which no honest person can make, but as the simple, astonishing fact that the question is finally in play. There is an ocean out there, under the ice, in the dark, that may or may not be alive. We do not know which. But we are no longer content to wonder from a distance. We have built the machine, chosen the world, and set out across the solar system to find out. Somewhere beneath 15 miles of frozen stone, in water that has never known a single sunrise, the answer is waiting, patient and silent, exactly where it has always been. And we are going, at last, to go and find it.